You know that feeling when you come home after an absolutely brutal day?
Oh,
Like you've been dealing with endless emails, stressful
just
meetings.
mentally spinning your wheels for 8 straight hours.
Exactly. And you collapse on the couch, look at the ceiling, and just say, man, I did so much work today.
It is a very universal feeling.
Yeah.
Total physical and mental exhaustion.
Right. But here is where it gets really interesting. Because if we were strictly following the laws of physics,
Uh-oh.
yeah, specifically the industrial physics used by instrument technicians, there is a very real chance that technically you didn't do any work at all.
In the scientific sense,
Uh-huh.
you might actually be right. I mean, you might have expended a massive amount of biological energy. You might be ready to pass out.
Right.
But if you didn't move a mass over a specific distance in a specific direction, well, zero work.
That is a tough pill to swallow. But that is exactly what we are unpacking today. We are taking a deep dive into the hidden physics of industry. We've got a stack of training modules here from NAT and SAIT.
Yeah, those are the heavy hitters in technical education up in Canada.
They really are. And this is material specifically designed for instrument technicians. These are the people who, install, calibrate, and fix the machinery that keeps refineries, factories, and processing plants actually running.
Right. So when they talk about work, power, and efficiency, they aren't talking about corporate buzzwords.
No.
They are talking about the hard math that keeps the lights on and prevents things from exploding.
So our mission today for this deep dive is to decode this holy trinity of industrial physics: work, power, and efficiency. And I want to start with that definition of work, because looking at these training modules, it's surprisingly strict.
It is incredibly rigid.
It feels like the universe just has very high standards.
Well, in this context, work is defined strictly as a scalar quantity.
Okay, wait, let's unpack scalar, because that sounds like something out of a sci-fi movie.
It does, doesn't it? But it's actually quite simple once you break it down. In physics, you generally have vectors and scalars. A vector has a direction attached to it, like north or down. A scalar just has magnitude, just a size.
So just a number.
Exactly.
Yeah.
Now, work is derived from things that do have direction, like force and displacement, but the final result, the work itself, is just a raw amount of energy transferred.
Yeah.
It doesn't point anywhere. It just is.
Okay, so it's a pure quantity of energy. But to technically perform this work, the text says 3 very strict conditions must be met. It's basically a checklist.
The 3 commandments of work. Number 1, a force must act on an object. You have to push or pull something.
Makes total sense.
Number 2, the object must move. There has to be displacement. No movement, no work.
And number 3.
The force must act in the direction of the displacement. This is the one that trips people up.
How so?
Well, if you push down on a heavy box, but the box happens to slide sideways, your downward push didn't do the work. Something else did.
Right, which brings us to what I call the zero work paradox. The source material has this great, somewhat frustrating example of a winch.
So the concrete block example.
Yeah, picture a heavy concrete block sitting in thick, sticky mud. You hook a steel cable to it, turn on the winch, the cable snaps tight, the motor is whining, it's pulling with everything it's got. But the block is stuck. It doesn't budge an inch.
Physically, the winch is exerting a massive force. I mean, it might be pulling with thousands of newtons. It's burning electricity like crazy.
Right.
But because displacement is zero, work is zero.
That just feels so wrong. The machine is clearly doing something.
It's doing something, sure, but it's not doing work. Think about it from the objective perspective. You haven't accomplished the task. You haven't changed the state of that block.
Because of the formula.
Exactly. The formula is simply work equals force times distance.
So W equals F times D.
Right. And if that D is zero, the whole equation just zeroes out.
That is brutal math. It really doesn't care about effort.
Not at all.
Yeah.
And all that energy that went into the winch, it didn't just disappear. It turned into heat in the motor windings. It maybe stretched the steer cable a little bit. It created a lot of noise. But it did not do useful mechanical work.
Now, let's talk about the units here. Because if we aren't measuring this in, sweat drops or effort, what are we actually measuring it in?
We're dealing with the joule. 1 joule is defined as 1 newton of force applied over a distance of 1 meter.
And just to ground us in reality, a newton is roughly the weight of a small apple, right?
Give or take, yes. So if you lift an apple 1 meter up in the air, you've done about 1 joule of work. It's a very small unit.
And the text does briefly mention the U.S. customary unit, strictly for context, which is the foot-pound force. But the training modules are pretty adamant about sticking to metric.
For very good reason. The math is just cleaner. You do not want to be converting slugs to pounds in the middle of a critical plant shutdown.
Definitely not. So we have force times distance, but there's a villain in this story, isn't there? The text spends a lot of time talking about the primary antagonist of work.
Friction, specifically kinetic friction.
Right. The source walks through this very practical scenario with a wooden pallet skidding across a floor. You're pulling it, you're doing positive work, but the floor is fighting back.
This is where we get into the concept of network. It's a crucial distinction for a technician. Let's say you apply 1,000 newtons of force to pull that pallet. That's your applied force.
Okay.
But the friction between the wood and the concrete floor is dragging back with, say, 800 newtons.
So you're fighting a massive headwind, essentially.
Exactly. You are putting in 1,000 newtons, but the net force, the force that's actually successfully moving in the object, is only the difference between the two.
Which is 200 newtons.
Right. The friction is actually doing negative work.
Negative work. That sounds like something I do on Friday afternoons.
Well, in physics, it just means the force is acting opposite to the direction of motion. Friction is stealing your energy and converting it into heat. It's essentially a tax on your system.
So if I drag that pallet 10 meters, I might feel like I did a huge job. But the useful work is only based on that 200 newtons of net force.
Precisely. The rest of your effort just warmed up the floorboards. And for an instrument technician, understanding this difference is literally life or death for the equipment.
Because of sizing.
Exactly. If you size an actuator, which is just a fancy motor that moves a valve, based purely on the load, but you forget to account for the friction of a rusty valve stem, that valve isn't going to open.
You end up with the winch and the concrete block scenario again.
Zero displacement.
And probably a very angry plant manager.
Indeed. Nobody likes a valve that stays shut when it's supposed to open.
Okay, so that's work. It's how much. But in the real world, how much isn't really enough. We need to know how fast. Like, if I hire you to move a pile of bricks and it takes you 10 years, technically you did the work, but I'm certainly not paying you.
And that takes us perfectly into power.
The rate of doing work.
If work is the destination, power is the speed limit. The formula changes from just force and distance to work divided by time. P equals W over T.
The source material uses the unit watts, which I think most of you listening probably know from light bulbs or maybe checking the back of a microwave.
Right. 1 watt is 1 joule per second. But remember, a joule is just lifting an apple. So 1 watt is a tiny, tiny amount of power. In an industrial setting, using a watt is like measuring a cross-country road trip in inches. So you'll almost always see kilowatts used, kilowatt used.
Or if you're old school, and I know a lot of the machinery out there still is.
Horsepower.
Yes, horsepowers. I love that the text includes this conversion factor. It feels like this bridge between 19th century mechanics and modern physics. 1 horsepower equals 746 watts.
It's a number every technician eventually just memorizes, 0.746 kilowatts. It's essential because the industrial world is a real mix of eras.
How so?
Well, you might buy a motor rated in horsepower because that's how they sold them in 1950, but your modern energy calculations or electrical inputs are all in watts. You have to be able to translate between the two languages flawlessly.
Let's look at the case study from the text. They have this scenario with a hoist lifting a control valve. And this isn't a small valve, it's 80 kilograms. That's like lifting a full-grown adult.
Right, and the job is to lift it 10 meters into the air, maybe up to a catwalk, and we have exactly 30 seconds to do it.
So walk us through the math here. How does a technician figure out if the hoist can handle it? Because you obviously can't just guess.
Well, step 1 is always gravity. Gravity never takes a day off. You have an 80-kilogram mass, so you multiply that by 9.81 meters per second squared to get the downward force in newtons.
Okay, so 80 times 9.81.
That gives you about 785 newtons of weight just hanging there.
Okay, so that's our force. Then we need the work.
Force times distance. 785 newtons times the 10 meters we need to lift it. That gives you roughly 7,850 joules of work to get that valve to the top. That's your overall energy budget.
But the real question is about power. Can we do it in 30 seconds?
Exactly. So you take those 7,850 joules and divide them by 30 seconds. You end up with about 262 watts.
That actually sounds surprisingly low.
It is very low. That's less than half a horsepower. But, and this is a huge but, maybe the biggest but in engineering, that is the theoretical minimum power.
The physics land power.
Exactly. In physics land, the chain has no weight. The gears have zero friction. The air provides no resistance whatsoever. In the real world, if you bought a 262-watt motor for this specific job, you'd be in serious trouble.
You'd burn it out immediately.
It would stall. It probably wouldn't even lift the load off the ground. This is why calculating the theoretical power is just the starting line. You need to know the baseline so you can apply realistic safety margins. You might need double or even triple that power to actually get the job done reliably day in and day out.
Which leads us perfectly into the third piece of the puzzle, the reality check, efficiency.
Efficiency is where physics meets economics. It's where the rubber actually meets the road.
The text is pretty blunt about this. It basically says you will never get out what you put in. It feels a bit pessimistic.
It's not pessimism, it's just the second law of thermodynamics. Input always equals output plus loss. And that loss is almost always our old friend, friction.
I noticed the formula for efficiency is really straightforward, though. It's just output divided by input multiplied by 100 to get a percentage.
Simple formula, very complex implications. You can calculate it using work, so work out divided by work in, or power out divided by power in. The result is exactly the same. It tells you how much of your energy is actually doing the job versus how much is just being wasted.
There's a deep dive example in the source that really blew my mind. It's an electric winch lifting a 200-kilogram flow meter.
Yes, the flow meter example. This one highlights the stark reality of industrial machinery better than anything else.
So let's run the numbers on it. The input, the actual electricity going into the motor, is measured at 4.5 kilowatts. That's what you're paying the electric company for. That's the utility bill.
Correct. 4.5 kilowatts is your input power.
But then they calculate the output power, the actual physics of lifting that 200-kilogram box against gravity, and it comes out to only about 1.96 kilowatts.
Right. You're paying for 4.5, but you're only getting 1.96 worth of actual lifting.
I did the math on that efficiency. It's 43.6%.
That's it, less than half.
Where did the rest go? That's over 2.5 kilowatts of power just vanished.
Well, it didn't vanish. Energy cannot be destroyed. It transformed. It became heat in the copper windings of the motor, heat in the bearings, sound energy as the heavy gears ground together, maybe even vibration shaking the mounting bolts.
That is wildly inefficient. Is that normal?
For certain types of simple machines or older mechanical systems, absolutely. Worm gears, for example, are notoriously inefficient.
Huh.
And this is why the expert perspective in these modules focuses on this so heavily. Think about a factory floor for a second. If you have a plant with hundreds of motors and they are all running at 40% efficiency, what are you actually building?
A sauna.
Essentially, yes. You are running a massive heating element that occasionally lifts things.
That's a really painful way to think about a factory, a giant heater that just happens to make products on the side.
Financially, that's exactly what it is. That 2.5 kilowatts of loss isn't just waste, it's a double liability. First, you have to pay the utility company to supply that power. It costs money. Then, because the motor is dumping 2.5 kilowatts of heat into the room gets hot. So now you have to run air conditioners or massive ventilation fans to cool the room down. You are literally paying to remove the heat you just paid to create.
So when an instrument technician is selecting a valve actuator or a pump, checking that efficiency rating isn't just about being green or environmentally friendly. It's about not bankrupting the facility.
Precisely. High efficiency means less waste heat and much lower operating costs. Over the lifespan of a machine, say 20 years, an efficiency difference of just 5 or 10% can easily equal the entire purchase cost of the machine itself.
That's incredible context. It really raises the stakes on the math. Now, I want to pivot to the applied problem-solving section of the source. This is where the rubber meets the road, or I guess where the rope meets the pulley.
The single pulley examples are great because they force you to combine everything we've talked about so far. Force, distance, and efficiency all in one practical scenario.
One thing that stood out to me here was the unit conversions. The source text really hammers home that you cannot just plug numbers in blindly. You have pound force, pound EF, and you have kilograms.
It's a classic trap, especially in North America. You have a technician who measures the pull force in pounds because he's using a standard mechanical gauge he grabbed from his truck, but the mass of the object is listed in kilos on the manufacturer's spec sheet.
The text gives the exact conversion. 1 pound force equals 4.448 newtons.
And you must do that conversion first before you do anything else. If you multiply pounds by meters, you get nonsense. Foot-pounds meters. It's not a unit. You need newtons times meters to get joules.
So let's look at the logic chain the text suggests for solving these specific problems. It seems to always start with the load. Why start there?
Because the load is the reality. The output work is the non-negotiable part of the equation. The rock weighs what it weighs. Gravity is what it is. That gives you the force of gravity. Then you look at how far you're actually moving it. That gives you the output work.
Right, so you establish the absolute must-have first.
Correct. That's your baseline. Then you look at the input. What do you actually have to pull on the rope? In the example, you might pull with 65 pounds of force to lift a 26-kilogram regulator.
And when you do the math, converting that 65 pounds to newtons, you realize the input force is higher than the output force.
It always has to be.
And the input work is higher than the output work.
Always. If you ever calculate efficiency and get 105%, you've either discovered perpetual motion or, more likely, you just made a math error. Usually you forgot to convert the mass to newtons.
Or you need to call the Nobel Prize Committee immediately.
Exactly. But in the real world, the input work is what you pay, the output work is what you get. The difference is the tax paid directly to friction.
It's interesting how these training modules structure the problems too. They explicitly ask you to calculate the friction loss, like determine the amount of heat produced.
I love that they phrase it that way. It forces the learner to acknowledge that heat isn't just a byproduct or a mistake, it's a highly quantifiable energy term. In one problem, the friction accounts for 10.8 kilojoules of energy, while the useful work is only 24 kilojoules. That's a huge chunk of the total energy budget.
It really changes how you look at a simple pulley. It's not just a wheel with a rope, it's an energy transaction point.
That's a really beautiful way to put it. Every machine is an energy transaction point. And as an instrument technician, your job is to make sure that transaction is as favorable as possible. You want a good exchange rate.
You know, we've covered the what with work, the how fast with power, and the how good with efficiency. But looking at this stack of paper, the thing that sticks with me is just how rigorous the definitions are. It feels like there is absolutely no room for interpretation.
That's the fundamental nature of the industry. Ambiguity leads to accidents. When we say a valve needs to close with a certain force or a motor needs to deliver a certain power, these aren't estimates. They are calculated based on these exact formulas. If you guess, things break. People get hurt.
So what does this all mean for you, the listener who might not be calibrating a flow meter tomorrow morning? Why did you care about scalars and friction coefficients?
I think it gives you a totally new appreciation for the hidden balance sheet of the physical world. Every time you hear a motor hum, every time you see a crane lift a steel beam, every time your washing machine spins, there's a constant, rigorous calculation happening in the background. Joules in, joules out, watts consumed.
And realizing that everything is fighting friction every second of every day.
It's the constant battle against entropy. We are paying for order with energy.
So here's my final thought for you to chew on. We talked about how efficiency is output divided by input, and the loss is due to friction. The text literally calls it work lost to friction. If we could theoretically eliminate friction entirely, I'm talking magnetic bearings, vacuum chambers, advanced materials we haven't even invented yet, would we achieve 100% efficiency? Or is there something else in the machine, some other ghost in the physics that demands a tax? And since we realistically can't eliminate friction entirely, does that mean that essentially every single machine in existence, your car, your blender, the massive turbine at the local power plant, is primarily a heater that just happens to do a little bit of work on the side?
That is a haunting thought. But technically, yes, we live in a world of heaters.
Thanks for taking this deep dive with us.
Always a pleasure.